So it's time to go to our next presentation. I personally am really excited to to hear and listen to the next presentation. Dr. Kenneth FURTON, Executive Director of Global Forensic and Justice Center at FIU and Chief Scientific Officer and Provost Emeritus, is going to talk about a very interesting topic, use of canines as a corrosion detection device. Dr. FURTON.
Thank you very much. Thank you for that introduction, and thank you for the opportunity. I think this may be the first canine project I think you probably had. Hopefully, I'm just going to share with you some of the concepts to get your feedback and suggestions, because it's early stages, but I hope to be able to convince you that that this could be a unique opportunity to utilize biological detectors for studying corrosion in bridges and for other applications. So let me just start. I also want to recognize Kelvin Frank and Howard Holness from the Global Forensic and Justice Center, who are collaborators on this project. And at the end, I'll recognize my collaborators within the College of Engineering. So basically, the relevance of this project is that canines have been really been reliably used for hundreds of years, and most people are used to drug dogs and bomb dogs or explosive detection canines, narcotic detection canines. But more recently, we've been using canines for things like mass storage devices and even microbe analysis. And in many cases, we're finding that there's even higher sensitivity and selectivity of canines than some of our instruments. So I think this is an opportunity to see whether this could be a tool that could be valuable to the construction industry generally, but also specifically for bridges. So I'm hoping that the research outputs would be a new cost-effective, efficient, and reliable method to detect corrosion, not any corrosion, but a specific level of corrosion in steel structures that could then be validated using instrumental methods. So here at FIU, we have over 30 years of experience in studying odors of canine targets. Accelerants is an example where when there's a crime investigation, they'll use accelerant detection canines, and they're calibrated to a certain level of accelerants, because you'll find trace amount of accelerants in the environment generally. And what we were able to do is to calibrate them to a level that would be consistent with a potential arson. And then those samples are actually analyzed in the laboratory or on site with an instrument to confirm the canine alert. So when I like to kind of show that there's a lot of different ways, orthogonal detection techniques, that can be utilized to look at volatile organic compounds coming from a source that you're trying to look at. Most commonly in the laboratory is gas methods, so gas chromatography, mass spectrometry, and that's the method we're going to use to confirm the volatile organic compounds, or the VOCs, that the canines are alerting to. There are also electronic noses, of course, that can be developed for use in the field. Optical techniques for non-contact, for standoff detection, and then biosensors. So dogs are the most commonly used biosensor, but I've actually been involved in projects where we've trained elephants to detect explosives. We've trained birds to detect explosives. So once you show the proof of concept, you can train other animals that might have useful applications down the road. So I like to basically say that biological and electronic detectors are complementary. So we're not proposing that detection canines would replace anything that's currently being done, but they could potentially be used as a screening tool to enhance locating areas where you would do additional electronic detection of a possible corrosive area to look at whether there's a concern or not. So there's always a balance. There are advantages and disadvantages of instrumental as well as biological detectors. Generally, biological detectors are still more selective, sensitive, quicker, and of course they're very mobile. and versatile and rugged. They can work for long periods of time in extreme conditions, and they can do standoff detection. So you do not have to be right at the source. They're capable of being trained to alert at a distance. So some of the applications, what we find is that rarely does a dog alert to the actual substance that they're looking for. They're alerting to these volatile organic compounds. So in the case of cocaine, it's methylbenzoate. In the case of ecstasy or MDMA, it's propirenol. For plastic explosives, it's 2-ethyl-1-hexanol. In the case of smokeless powder or dynamite, TNT-based dynamite is 2,4-dinitrotoluene. While you're alive, it's things like furan carboxaldehyde, and when somebody is deceased, it's other compounds show up like dimethyl disulfide. And just to show you an example of one project we worked on is the level of odor detection that dogs are capable of is really remarkable. So this is a case where you see on the left, we had a truck that we had a person, a driver, and a passenger touch the vehicle, walk off into a desert area. We detonated 5 kilograms of a hydrogen peroxide, a nitromethane explosive device, and completely destroyed the vehicle, collected fragments, and the dogs were able, 8 out of the 11 dogs that we tested were able to positively follow a trail from the detonation site to the either the decoy or the target at a distance in this desert conditions. The materials we collected, we weren't able to determine that there was any human scent on the devices, but the dogs were still able to do it. So in some cases, some people think it's magic, but it's really not. It's science. This is all was double-blind, tested. It was published. It's even videotaped. But I still actually find it remarkable that the dogs are capable of such low levels of detection. During COVID-19, we were one of the first at FIU in the country to train dogs for COVID-19. So we worked with Baptist Hospital. We basically used UV light to take masks from patients at the hospital that were COVID positive and those that were COVID negative. The UV light made the virus inactive, and we were still able to train the dogs. And what we do in the laboratory, on the upper right, you see chromatograms of positive and negative patients, and you can clearly differentiate them. And then we trained them on that wheel that you see at the bottom, excuse me, with the masks basically in those containers. And what happened was we actually found, so if you look at just doing a PCA analysis, you can clearly see the difference between positive and negative masks on the left, and then the accuracy of the dogs is shown on the right. So the overall accuracy was 95.9% for the 4 dogs that we tested. And this was 2 purebreds, a Dutch Shepherd and a Belgian Malinois, and then 2 rescue dogs, a Terrier mix and a Border Collie mix. But they were all very accurate. Actually, in accuracy, it exceeded that you would actually see with PCR tests. And then most recently, we've been working to kind of demonstrate to you the low level of VOCs that can be detected. Is in the past, we had dogs that were able to detect currency because people would be, using larger amounts of currency going back and forth through the airport, or they might be hiding currency. Now, of course, they're storing either their crypto wallets or sensitive information on electronic mass storage devices. And so what we've been doing is looking at the headspace of these samples. We use something called solid phase microextraction, and then we put it in the GC mass spec, and we identify the compounds, the relative VOCs, and then work with the dogs to show are they able to find these devices reliably. And this is actually an example of a Miami-Dade Police Department has we certified detection canines. So this is a certified mass storage device detection canine. And they've had numerous cases where a very small flash drive or different kinds of storage devices could be hidden even in a warehouse, and the dog will search the entire warehouse and be able to find that. Or in homes, they'll be able to find, extremely small electronic devices that are hidden away, let's say, in a filing cabinet in a very large home, which would be very difficult to do even if you had an electronic detector. So the idea here is the first task is really just to train the dog to detect the target odors in concrete structures. So we'll start with what we use is called the Universal Detection Calibrant, or UDC. This is something that we developed and it's patented through FIU. That can be used to calibrate instruments, and we use it to essentially calibrate the dogs. And this UDC will be placed inside a perforated canister, and then that will be encased in a concrete structure. And then we'll currently we're training these dogs on the UDC. They'll be trained to recognize the UDC inside these concrete structures. The second phase is actually identify the VOCs from artificially corroded steel. So we'll use our analytical instruments to identify any VOCs that we can identify, looking at various levels of corrosion using, again, this headspace solid phase microextraction GC mass spec method. And then we'll be looking at the intensity of the components and the degree of corrosion to see what level we would want to imprint the dogs on, essentially to calibrate them at a particular level. The third task would be to utilize the targeted corroded steel for canine imprinting, so training the dogs on the corrosion. So we would look at the appropriate corroded steel from the previous task, and then we will, at the moment, we have 3 dogs that we've identified that we can train to complete this task. And then the fourth task would be validating of the corrosion detection using the trained canines. And this is, we'll test the ability that those dogs that we train in task 3 can actually detect the odor coming out of encased concrete structures. So just a little bit about the universal detection calibrant. It's a material that's it's a volatile chemical not found in the environment, and it's not part of any other of the dogs, any other odors in the dog's repertoire. So if they could be trained, let's say for agriculture detection or electronic devices, then we can also keep them calibrated on this bromo-octane. So there's a number of different compounds we can use for UDC, but bromo-octane is the one we're using in this study. This is housed in a permeable polymer, which is known as a controlled odor mimic permeation system. So it gives a known amount of the VOC will be coming out. And so it allows us to have a targeted odor delivery. Well, we've never tried to permeate this through a material like concrete. So that's where we're at right now in terms of that testing. So here's sort of a visual of what it looks like. This canister on the left is the where the universal detection calibrant is housed with the perforation. Then this is placed in a low density polyethylene bag, so it protects it from getting clogged up with dirt or water or other materials, but the odor still permeates in one direction through that low density polyethylene. And then we'll be creating these concrete cylinders. Here's the concrete cylinder mold, and the UDC canister will actually be encased within that concrete cylinder. And that's what we'll be using to look at the VOCs coming out, as well as using it for training the canines. So as I mentioned, we'll expose 3 previously trained canines to these concrete cylinders. So these are dogs that we know can reliably find the universal detection calibrant. They've typically been trained for other odors. For example, we've used them to look for the fungus that causes laurel wilt that kills avocado trees. So as long as you're using a target that's different than the areas of, if dogs are trained to look in, let's say, an agricultural area, they could be used also for bridge inspection, and it wouldn't be a conflict because you wouldn't find the same odor in the 2 different areas. And this is the timeline that we're anticipating. By the end of this year, calendar year, we expect to have had the ability to for the canines to detect the odor in the concrete, the universal calibrant, the UDC. And then the beginning of 2023, we'll be completing the VOC analysis of corroded steel. Then we'll be training by the mid part of next year the dogs on the selected corroded steel samples at the levels that we expect might be useful for application. And then by June, we will have the canine detection of the corroded steel samples in the actual concrete sample. That's what we're expected for our time frame. And with that, I want to wrap up by thanking Dr. Kinsley Lau from Civil and Environmental Engineering. He's collaborating on this project, on all the guidance on the corrosion work, and we're utilizing his lab for most of the relevant work. And Dr. Patrick Roman from the AMERI, who is assisting with the manufacture of the perforated canisters, and is also collaborating on this project. And of course, I want to thank my research group. The person on your far left is Calvin Frank. He's the one that's primarily working on this project. And the person on your far right is Howard Holness. He's the director of research for the Global Forensic Justice Center, and he's also a collaborator from the Institute. And with that, I think I've left plenty of time for questions.
Thank you very much, Dr. FURTON. Indeed, I mean, I'm amazed with the amount of the work that has been done before, and why nobody thought of this before to smell the corrosion. I saw that you are basically the task that you set up is targeting steel corrosion inside the concrete. Is that true, or is it also including exposed steel corroded, basically?
At the moment, we were looking at the steel corrosion within embedded within concrete, but we could look at exposed steel as well. That would actually be much easier to do, maybe even as a first step, because the concept was we're trying to replicate having the odor, let's initially the UDC, and then the steel, corroded steel, at a depth within the concrete that you might find within a bridge structure. So that's why we designed it, actually being embedded within the concrete, but we could do exposed steel as well.
I see. Some people may ask, why do we need then something else to see the corrosion on a steel when it can be, I mean, we can see it by naked eye. But again, those of us who have done inspection in tight spaces inside the bridges, etc., would really appreciate having something like that rather than them trying to crawl into the bridges and things like that. So there are really, I personally believe there is a need also for detection of corrosion that is obvious, but not in a space that is accessible easily accessible by humans. Anyway, thank you very much, Dr. FURTON. We'll be looking forward to the more results in our next research day, which will be sometime in next April or May. What I also wanted, before we go to next university, we are done with presentation from FIU, but before we go to University of Oklahoma, I wanted to mention for all these projects which belong to Cycle 5 of 2016 grant, these projects have started just a few months ago. So that's why we are featuring them with some progress, but we will see more progress in our next research day. And we believe that this is the time to talk to others if they have input, so that those inputs can be addressed during the research project. Thanks again, Dr. FURTON. We appreciate your time.